We're going to do more with series and determining whether they converge or diverge. Today, we're going to look at the comparison tests. Now, there are two of them. First one is often just called the comparison test, or sometimes it's the direct comparison test. And so this goes back to our whole idea that if we have a bigger series that converges, a smaller series must also converge. If we have a smaller series that diverges, a bigger series must also diverge. So it's figuring out using common series that we know things about, specifically like the P series or a geometric series, to then say, okay, what's happening with this other series that looks similar but has some differences? So our direct comparison test, it says that we have our A series and our B series. But they all have positive terms. Now, this can also be done if they all have, if this terms are all negative, we can factor out a negative and do stuff there. But we're just going to stick with the positive ones for this. We'll worry about some negatives later on with other tests. So our first one says that if the B series converges and A sub n is less than or equal to B sub n for all n, especially greater than or equal to 1, then our A series will also converge. Now, there is a way around this if A is bigger than B in certain situations, but it's a little bit easier just to make it the blanket statement if we say for all. On the other hand, if our A series diverges, and our A is less than or equal to B, for all of our n, then the B series diverges. So again, if the big one converges, the small one also converges. If the small one diverges, the big one also diverges. We can't say anything else, though, if it goes the other way. If the small one converges, don't know about the big one. If the big one diverges, can't say anything about the small one. Because the little difference between the two might make the big one diverge, but maybe it's not enough and it still converges. The small one might lose enough that it will converge, but then maybe it doesn't and it still diverges. So we can't say anything. So let's go with this one. So 5 over 2n squared plus 4n plus 3. We're going n from equals 1 to infinity. Does it converge? Does it diverge? Now we could try to figure out, hey, does this or is this a telescoping series and try to figure out the exact value for it and go from there. But an easier way is to take a look at our terms of this series. Now it's important that whenever we do this comparison that we drop our summation. We don't want to have the summation because we're talking about the terms here first, then we can talk about our series altogether. Now this would be less than or equal to 5 over 2n squared because we're adding some stuff here on the bottom. So therefore, we're making the bottom bigger, so the whole thing would be smaller. And now the summation of n equals 1 to infinity of 5 over 2n squared is the same as 5 halves summation of 1 over n squared. And this one will converge because it's a p-series. P equals 2, which is greater than 1. So again, make sure you tell me what's happening, tell me the test you used, and tell me how you evaluated that test. Next, since we have this relationship up here, we can then say that our series will then be less than or equal to our p-series that we just talked about. So we're using a direct comparison test. Therefore, since our p-series converges, the other one will also converge. Let's do another one. Let's say we want to do n equals 1 to infinity of natural log of n over n. And often you'll see whenever they use natural log, they'll change your n to your n here as your index into a k, just so you don't confuse it with the n from natural log. All right, so let's think of what can we do here. One, this would set up the for a very nice integral test. So often you can use different tests to figure out convergence, divergence. And as you're practicing, that's a really good way of doing it, of doing those when you see that you can use multiple different tests, do all of those tests in your practice. That way you can, one, verify that you're doing them correctly, that you're getting the same results. And two, it gets you, let you evaluate, okay, which of these tests would be easier to do? Should we do an integral test? Should we do a direct comparison test? Should I do a limit comparison test? What should we do? And then whenever it comes time for a test or a time situation, you can then choose whichever method works the best, as long as the directions don't say otherwise. All right, so for this one, since our bottom is just an n, we could compare this to our 1 over n. However, this only works as long as our n is greater than or equal to 3. So we have a little bit of an issue with that we're not starting from 1. But again, it was only for a finite few. that we don't have this in there in the beginning, so therefore we can let that slide. So the summation for n equals 1 to infinity of 1 over n will diverge. And there's two ways of thinking of this. One, you could cite that it is the harmonic series. And that's enough. Or you could say that it's a p series where the p is 1, which is less than or equal to 1. So therefore, it diverges. Then doing our comparison, since we know that our smaller series is diverging, the bigger series will also diverge, and this is for a direct comparison test again. So whenever you do your direct comparison test, always make sure you justify why the simpler series converges or diverges. So make sure you do this justification, give the test that you are using. All right, but this is not always going to work. So say we wanted to figure out this 1 over 2 to the n minus 1. Now it looks kind of like a geometric series. So if you wanted to compare it to 1 over 2 to the n, we can tell whether or not that converges or not. But in this case, our bottom is smaller because we're subtracting something, so it's bigger than our comparison. Since our comparison is going to converge, we can't say anything about the bigger one. So the direct comparison test does not work. However, they're going to act in similar ways, so we should be able to do some type of relationship. In this case, we're going to use what's called the limit comparison test. And the limit comparison test is, I think, a little bit more versatile than our direct comparison test. Because the direct comparison test, you must have your relationships in the correct order. You have to know if the small one diverges or the big one converges. For the limit comparison test, it doesn't matter which one's bigger or smaller. They just need to act in a similar manner. So we have our two series, our A series and our B series. And these both have positive terms again. If we get some that bounce back and forth from positive to negative, we have to use a different test. All right. So if the limit, and here's why it's the limit comparison test, as n goes to infinity of a sub n over b sub n equals some value C, where C is greater than 0 and C is finite. So it can't equal 0 and it cannot be infinity. Then both series either converge or diverge. So it's a follow the leader. That whatever the first one does, the second one's going to do the exact same thing. And it does not matter where you put your function in comparison to the one that you know about. Since we are doing fractions and we're comparing to 0, if you would do your fraction one way and you would get a result of a half. If you would flip it, you get a result of 2. Either way, you're evaluating the results the exact same way. So the order of your fraction really makes no difference whatsoever. Now, on the other hand, if you would set this up and do a bad comparison, then doing it one way, you might get a 0. And if you flip it the other way, you would get an infinity. So still, you're getting an inconclusive result from your limit comparison test. So order doesn't matter still. All right, so let's go back to our example we just looked at. 1/2 to the n minus 1. And we're going to compare it to 1/2 to the n. Now, if we rewrite this, it doesn't matter if the 1 on top has a power or not. So this is essentially 1/2 to the n power. Therefore, this is a geometric series. Our r is 1/2, which is less than, or well, it's between -1 and 1. So it will converge. So therefore, if we do the correct comparison with our 1/2 to the n minus 1, it should also converge. So let's do our limit as n goes to infinity. And the book sets it up as the 1/2 to the n is the on top one, that's your a. I would do it the other way. Or say it does 1 to the 2 to the n minus 1 is on top. I'm going to do it the other way, and you'll see why. Now, dividing these fractions, we're going to get 2 to the n minus 1 divided by 2 to the n. Now, since our subtractions in our numerator, we could split this up and have it be 1 minus 1/2 to the n. If our subtraction's on the bottom, we can't split this up, so this just makes our process a little bit easier. Then, since our n is going to infinity, 2 to the n is going to go to 0, so our whole thing is going to equal 1 as a helicopter flies overhead. Now 1 is greater than 0, and 1 is finite. Therefore, since our 1/2 to the n converges, our 1/2 to the n minus 1 will also converge, and we are using the limit comparison test. Now, while the direct comparison test, sometimes they drop the direct and just call it the comparison test. Not that way for the limit comparison test. We must say that it's the limit. All right, let's try another one. So let's do the summation of n equals 1 to infinity of 2 to the n squared plus 3n, or 2 times n squared plus 3n, all divided by the square root of 5 plus n to the fifth. All right, so this is kind of a mess. So in order to try to do some comparison, because the integral test isn't going to work, let's go ahead and just focus on the numerator and denominator and find our leading terms. So where do we have the biggest exponents? So what would happen if we did a 2 times n squared, all divided by square root of n to the fifth? If we simplify this, that bottom would be n to the 5 halves. And then doing a subtraction, since we're dividing our fractions, it's 1 over square root of n. Or if we wanted to pull out the 2 and change it, it's going to be 1 over n to the 1/2 power. And make sure your exponents look like exponents there. Personally, for this one, I would rewrite that a little bit to make it clear so that as an explicit exponent and not being multiplied. Make sure you can read your writing. Also important thing, make sure with your fractions that that division line covers everything. That it fully underlines the numerator, fully overlines the denominator. Make sure that your square roots fully cover everything that they're supposed to cover and nothing that they're not supposed to cover. All right, so now our comparison setup here, this one is going to diverge because it is a p-series, and our p is a 1/2, which is less than or equal to 1. All right, so let's compare it to the other one. Now our bottom is bigger and our top is bigger, so it's kind of inconclusive. We could use the method we did before of setting our two comparison things equal to each other and cross multiply and then go from there. But rather than that, we have our nice setup here. In this case, it's not going to make much difference which one is our numerator, which one's our denominator. I'll put the original as our numerator just because there's more to it, so I don't have to flip that. And then let's do our simplification a little bit. So we have 2n squared plus 3n times, and just to make it a little bit easier, square root of n all over square root of 5 plus n to the fifth times 2. All right, a little bit messy in there, but let's go ahead and distribute. So an n to the 1/2 times everything. So it's 2n to the 5/2 plus 3n to the 3/2 all over 2 square root of 5 plus n to the 5th. We have a couple ways to handle this. You could try L'Hopital's rule, but that square root's going to cause you some issues. So let's try to factor out an n to the 5/2 power. Here we get 2 plus 3 over n on top. On the bottom, we would get our 2n to the 5/2 square root of 5 over n to the 5th plus 1. Those cancel. As our n goes to infinity, this goes to 0, that goes to 0. So we're left with 2 over 2 times the square root of 1. This is greater than 0. 1 is finite. Therefore, our summation will diverge by our limit comparison test. And I recommend writing out the entire name of it. Don't use abbreviations, just so everyone knows what you're talking about. And we can also do an estimate of error for these, just like what we did before. If you would like to see how close you are to the actual sum. Now be careful this works for your converging series, because if it's divergent, it's going to infinity anyway. So not worry about that. But you would do things in a similar manner. But important things here are that we have now two comparison tests. If we know things about certain series, specifically from the geometric series or our P series, that we can use that information to see what's happening with similar series that look kind of alike it, but are a little bit off. We can do a direct comparison if we have things in the proper order. If our bigger one converges, the smaller one will converge. If the smaller one diverges, the bigger one will diverge. Or we can, if we don't have the right order on that, but we still know something about a similar series, then we just use a limit comparison test, but make sure that your limit is indeed a finite number. If you use the wrong comparison, then your limit will give you either a 0 or an infinity, which means try a different function to do your comparison.